Hello everyone and welcome to another AP Computer Science video. This video we're going to focus on the second half of our discussion of searching and sorting. We talked about sorting data, putting it in a particular order based on comparisons we can make between values. We did our example with an array of integers, but we mentioned that we could do the same work with arrays of strings or array lists of objects. There is no kind of limitation. As long as we understand how to compare values, we can implement some sorting algorithm. The three that we saw, bubble, insertion, and selection, are not particularly good sorts, but they are all functional within a certain limitation of items. Insertion was the best of the three, and we'll come back around to this when we do a little bit more. When we finish up the course, we'll talk about one more sort and how it's significantly better overall than these three. But with that said, we'll finish up with the searching aspect, because sorting data is great, but putting it in a particular order, usually there's a reason. And one of the reasons might be, if we put data in sorted order, it might be more effective to search through. And so the idea is that we want this ability to look for things. This is a very common situation. I have a bunch of information. Do I contain what I'm looking for? For example, if I have a list of student names and there are tens of thousands of students, I want to be able to say, can I quickly establish, do I have this student's information in my collection or not? And so the ability to search for things is important. And we're going to talk about two broad types of searches, and really we'll come around to why the sorting becomes important with the second one. So we're going to make a new class in our searching and sorting package, and we'll call this one searching examples. So there are going to be two types of searches. The first one is the easier one, and we've done this already. We've already had the ability to search through an array or an array list. We'll do these examples with array lists just so we can see some array list methods and be comfortable. But we'll go ahead and talk about everything in terms of array lists of, still do integers, but we'll go ahead and make this work with an array list of integers as opposed to an array of integers. So I'm going to go ahead and set up our main method like we always do. But before we fill it in, let's go ahead and make an array list and add some numbers to it. So we're going to say an array list of integers. And remember, when we make an array list, we have to use the wrapper class in our diamond notation. We'll call it list. We'll call the constructor. We need to fix our imports to make sure that we import the array list class because we know it's part of what we're using. And then let's fill it in with a bunch of random numbers. So let's go ahead and do that. Let's go ahead and put in maybe 100 or 20 different numbers. Int I equal to 0, I less than, we'll put 50, I plus plus, and we'll do this. We'll say int ran is equal to a random number between 0 and 100. So that gives us a number between 0 and 100, and then we'll add that number to our list. List.add. And again, I'm adding to the end, so there is no particular order. So this is the first thing we're going to note, is the first type of search is essentially effective when it's random data. It actually works no matter what the data order is. The second one, which seemingly is the better one, but only works on the assumption that our data is sorted. So we'll see that in a moment. And so with this, if I print out this list, we haven't seen it yet, but conveniently, we could loop through each value and print out each value, but array lists can be printed directly, and it'll conveniently give us a nice display. So if I simply print out the list, we should see all the numbers that it generates. And every time we run it, because it is random, we should see different values. And so let's make sure that's the case. And we can move on from there. So there it is. 50 numbers, randomly generated. I'm going to run it one more time, and we should get a different set of numbers. And there it is, 79, 16, 31. If I run it one more time, we can see we probably won't get 79. So there it is, different each time. Okay, so we have our list of numbers. Now, let's make a method. The goal here is to make a method that, given a value, finds the index of that value if it exists. So this is kind of like index of in a string, the method. It says look for something, and if you find a match, return the index where you found it. And if you don't find a match, then return -1, because -1 can never be interpreted as an index, so that's very convenient to return as a value. So, search through the list and return the index of the first matching value. So if there are duplicates, our solution is not going to find multiple spots, but only the first spot that it matches, the first matching value. So if we have a list of random numbers and there's two 17s and we look for this number 17, wherever the first 17 shows up, that's the index we're going to return. And we'll say if no match is found, return -1. And so we've done this before, looping through our content and saying, hey, are you the value I'm looking for? Hey, are you the value I'm looking for? And if you are, then we return the index that we were at. And if we're not, we move to the next one. And if somehow we do not find a match, then we return -1. So this should be an easy thing to do. Our signature, public, static, int, because we're returning an index, which is an integer value, or -1, which is also an integer value. And I'm going to go ahead and call mine linear search. And our input is an array list of integer values. And again, this could be arbitrary. It could be any data types as long as we know how to make comparisons. And so we'll call it a list. And so if you like, pause the video, take a moment, and search through the list and check if you find a match. If you find a match, you return the index. And if you do not find a match, then you return -1. Okay, so if you pause the video and you did this, now we can see my implementation, and hopefully we'll be able to establish how close you were and if you were right or not. And again, I think we've done it before. We did it with arrays. The idea is very, very similar. We're simply going to loop through every spot. I cannot use an enhanced for loop, even though that would allow me to see the values in the list. I am concerned about the index, so I need that sentinel value. So a regular for loop or a while loop with a variable might be the most appropriate choice. So I'm going to use a for loop. I'll start off at 0, which is the first index of the list. As long as we're within the size of the list, we won't go out of bounds, and we'll go up by 1 each time. And we'll simply ask the question, if the current value that I'm looking at, the ith value, is equal to the one I'm matching, so we're missing something. Of course, I forgot to put this in my signature. We should also take in the thing we're looking for. So int val, there it is. And so if the value happens to match the ith item, and we retrieve an item from a list with the get method, then all we need to do is return I. Right? So if there was a match, the first match, starting from 0, we return the index that we found the match in. And if there wasn't a match, then the if statement would be false, and we would move along, and we would iterate, iterate, iterate. Eventually, either we would hit a match, or if we didn't, we would get to the end of the list, the loop would be over, and if we somehow make it to outside of this loop, that implies we never found a match, and therefore we can return -1. And there it is, right? So search for the match. If you find it, that's the index, and that's the answer, and we're done. If there isn't one, then return -1. So now let's go ahead and try doing this. Let's go ahead and print out found index. And let's attach the method called linear search. We'll pass in our list, and we will pass in, let's look for the number 17. So there it is. And so if we don't find the number 17 in our randomly generated list, we should get -1. So let's go ahead and try this. -1. If we search, so again, it's in random order, so we have to kind of look for it, and I don't see it anywhere. Let's maybe run it a few times, and hopefully we'll find a match. And there it is, at index 35. So if we look at index 35, there it is. The first match is 17. We can count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on, and it ends up being at 35. So this does in fact work properly. And if there was more than one, then great. And let's run it again just to see. 23. And there it is. Right? Let's run it one more time. -1. And here there is no 17. I'm going to run it one more time. -1, right? So if and then I can be smart and search for it and say there is no 5. So if I look for 15, there it is. So it does work, right? And so now linear search is great. It will search through an entire list of values, or an array of values, an array of strings, an array of bowling balls, an array of bank accounts. As long as whatever our comparison is makes sense, then we can do that. Now, one kind of limitation, and why is it called a linear search, is the amount of searching or comparisons we have to make is equal to, or the same as, on average, the length of the list. If there are n items, we typically have to look at n things to find a match. In the worst case scenario, we look at all n items. So if there are 1 million items, we might have to look at all 1 million items and then establish that we haven't found it, our match, and then we have to return -1. So there's no skipping around. There's no trick that we can use, and so it's linear because the relationship between the number of items and the number of comparisons we make is a linear if the first one grows, the second one grows. It's a linear relationship, and so it's limited in how fast it can be. There's no tricks that we're using. But with that said, it works with any data. The data is random, it works. If the data is in sorted order, it works. If the data is in reverse sorted order, it works. So even though it's not spectacular in some situations when it could be, it's going to work no matter what. And that's a pretty good worst case scenario. If we don't have control, so basically if we as the user or the programmer that uses a search or needs to search don't have control of the data and have no guarantee of its ordering, then linear search is the only thing we can do to find something. Right? It can be an expensive operation, and if we're going to do a lot of searching, then it might be worth what we're going to do next, which is maybe sorting data and then searching through it with a special search, which we're going to call binary search, and we'll see in a moment how it's going to work. Right? So this is pretty good, but it is limited in the sense that even if we have a great sorting and we know some trick that we can have, we can't use it. We're going to look at every item on average, and so it's not going to be the fastest in some situations when we can do better potentially. So with that said, we're going to do the same thing. We're going to go ahead and say a binary search, right? And so the binary search is in fact the same. The goal is the same: to look through the list and return the index where we find a match. However, the trick here is the binary search makes one very bold assumption, that the data is in an order that can be recognized. For our implementation of binary search, the assumption we're going to make is that the data is sorted from small values to large values. If we make that assumption, we can implement it in an effective manner, and it will be significantly faster than the linear search, particularly with large data sets. And then, of course, we would have to make the effort of sorting. And if our sort is bad, then it would also, not work out so great. But we have to decide that. Same goal as linear search, but assumes the data sorted order, which allows for a much more efficient implementation. Right? It must be in sorted order. We must know the order in some fashion. So here we go. Public static int, because we're still returning an index, and we'll call this one binary search. And the same as before. We'll take an array list of integers. We'll call it a list, and then what we're looking for. And so now, if you happen to know how to do this, if you know a trick that will make this work, you could try implementing it. But if you don't, then we'll just discuss the algorithm together now. The goal is going to be, if we think about it, if we have our data in sorted order, so for example, if I just made a list like this, if I had the number, 3, 5, 6, 6, 8, 13, 15, 21, 35, 38. If that was my list of numbers, and I pick any number, what can I say about any number? So if I'm looking for the number 26, I want to know if it's 26 in this list, and I pick some random number to start with, what can I say about the fact? Can I make some guess as to whether or not I'm going to find the number, or where I should look for the number if I know something about where I've chosen? And the answer is, if it's in sorted order and we can make that assumption, then we know if this is not the number we're looking for, we can at least say either it's to the right of it or to the left of it. So if I'm looking for 26, I only have to look to the right side of 6, because since 26 is larger than 6, there's no way it's possibly on the left side. So I've basically eliminated half, or almost, or in this case, I've eliminated 3 options. So now I'm looking from here to here. And let me just pick this one. Okay, well, is that the number I'm looking for, 26? And the answer is no. So is the number 26 bigger or smaller? And if it's larger, then I only have to look at the right half. So I've eliminated now 8 to 15. and the 21 because it wasn't a match. So now I only have to look at 2. And so in reality, looking for the number 26, the way I did it, I only had to make maybe 2 or 3 comparisons, which is significantly less than the number of items there are. I didn't have to check every one. Why? Because I can ask the simple question, well, if you're not the number I'm looking for, is the number I'm looking for bigger or smaller than the current value? And if it's bigger, then only look to the right of it. If it's smaller, only look to the left. Essentially, we're splitting the groups into 2 possible groups, those that are smaller than the answer that we're at, or those that are larger. And every time we split it, we're cutting out half the numbers until either we find the answer or we don't. And so either way, the searching through only half of the work each time makes us significantly more efficient than a linear search. If a linear search says there are n items, so on average you're going to do n comparisons, the binary search says if you have n items, then it's going to take log base 2 of n comparisons. So this may not seem like a big difference, but the log base 2 of n compared to n is a huge factor smaller. In fact, the log base 2 of a billion is only about 30. So a linear search would say if there's a billion numbers, I might have to look through all 1 billion numbers just to find out that it wasn't there. That's really slow. A binary search would say if you have a billion numbers, at most you're probably going to have to look at maybe 31 comparisons. That's a lot smaller than a billion, so that's way faster. But of course, the assumption was that the data was in order. So if the sort was expensive in terms of time, then the search maybe is not great. So when we choose which one we're going to do, it's really about the data. If you're going to be searching a lot, it's worth sorting it and then using binary search. If you're going to search one time, then there are many situations where linear search is good enough. So those are decisions that programmers have to make. But either way, we should have a comfortable understanding of the implementation of the binary search. And so the trick that we're going to do is instead of just guessing where I'm going to start, we're going to pick the middle every time. So the middle of this one, how many items are there in this list? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The middle, I'll say, is halfway in it. So 10 divided by 2 would be 5. 0, 1, 2, 3, 4, 5. In reality, is that really the middle? No, because that's 6 values and then 4 values, but it doesn't matter. So roughly the middle. And then I'm going to say, is this what I'm looking for? If it is, then I'm done. If it's not, then I'm going to say, is it smaller or bigger? And that'll put me in one of the other sections. And then that saves me the work, and then I repeat the process. And the only time I stop is when there are no more values in my list. So what we're going to do, to make this work for any size, we're going to always keep track of where's the start of where we're searching and where's the end. So initially we're going to say look from 3 all the way to 38. And then we're going to eventually say we'll only look from 3 to 13 or 3 to 8 or from 15 to 38. And we're going to shrink those things. So let's make 2 variables that keep track of those different edge case indices that we're going to deal with. So we're going to say upper, we'll say int upper, and we'll say int lower. And I'm going to put these in 2 variables just so we can read them. So we're going to say upper, the class index to search through first. Well, actually, let me be better than that. Let me write something better. We'll say the largest index of the range we are searching. And then we'll say the smallest index of the range we are searching. And then we'll initialize them. The first time we look through the list, we're looking at the whole list. So we'll say upper is equal to 0. I'm sorry, upper is equal to, let me do lower first. Lower is equal to 0. So that we start the bottom, which is 0. Upper is equal to the list.size minus 1. So those are the indices. So if I'm looking from index 0 to index size minus 1, that's the whole list. And then now our condition is very simple. We're going to say, you know what? Keep searching as long as the lower is strictly smaller than the upper. If at any point they cross, then we know that we've run out of things to search for, so we're not going to find our answer. So while lower is less than upper. And so if this is true, then we can keep searching. So if it's between 0 and 5, that's okay. If it's between 5 and 10, that's okay. But at some point, if they flip or equal to each other, then it doesn't work out. Then we've not found our value. So the goal is going to be simple. We pick the middle between the lower and the upper, whatever those values happen to be. So we'll say int mid. And just to note, these are indices. These are not values. These are not the content, not yet. We're only looking at indexes for now. So we'll say the middle index is equal to, And I mean, there's a lot of ways we can do it, but we can just add the two values and divide by 2. And let's just verify that. So if the entire length was 10, and this is 9, 9 minus 0 would be 9. 9 divided by 2 would be 4. So that would give you 0 to 4, and that would be that range. So again, it's not perfect. This one has 4, that one has 5. It's going to basically, if I do the lower plus upper divided by 2, we're going to always get the first half is smaller by 1 if it's an even number, which is fine. It doesn't really matter where it falls. So that would work out for here. But what happens if, let's say, lower was 5 and upper was 9? 5 plus 9 is 13. 13 divided by 2 is 6. So this is 5, 6. Oh, sorry, this is not 5. 0, 1, 2, 4, 5. Yeah. No, 5, 6, 7, 8, 9. Yeah, 5 plus 9. Sorry, 5 plus 9 is 14. No, am I crazy? 5 plus 9 is 16 divided by 2 is 6. No, that's not right. 5 plus 9 is 14 divided by 2 is 17. Is 7, sorry. 7, which is this one. There it is. I'm sorry. I don't know why I can't do basic arithmetic. But 5 plus 9 is 14 divided by 2 is 7. So this would be the middle, and then this would be the left half, and this would be the right half. That makes sense. I don't know why I couldn't do that. So we're going to do the lower plus the upper divided by 2. That's the middle thing. And let's just verify that it does work on the second half. Let's say our upper was 5 and the lower was 0. 5 plus 0 is 5. Divided by 2 is 2.5, or 2. 0, 1, 2, that's the middle. So that works out. It works out for both the upper edge or the bottom edge, the left and right side, so it works out no matter what. So we find the middle, and now we can ask our question. If the value at the middle index is what we're looking for, then we're done. We return the middle index. We found a match. And if it wasn't a match, then there's two possibilities. The value is smaller than the middle value or larger. So if val is less than the middle value, if that's the case, then we only have to look at the left half. So the upper bound is going to shrink. So the upper bound becomes the middle minus 1. And why is it minus 1? Because we already checked the mid-index, so there's no need to include it in the next one. So in this example of 0 to 9, if I was looking for the number 4, then we would find the middle first. It would be the 13. Oh, sorry, it would be the 8. And then 4 is not equal to 8, so we would skip this one. And now 4 is smaller than 8, so now upper would become 0, 1, 2, 3. And then now we were looking from 0 to 3. And that would be our new range, because if it's not this number, then it can't possibly be any number afterwards. And then we've just cut out half the work. And then we would find the middle of this one, which would be the 5, and then we do the same process again and again. And the only other possibility, if it's not equal to it, and it's not smaller, it must be larger. So I'll put the note here. We don't have to ask the question, but I'll put it, must be larger than mid value. And so here, the lower bound would change to mid plus 1. Because again, we're not going to include the middle because we already checked it. And that's it. This is the algorithm. The last step, of course, is if we somehow do this again and again, at some point they might cross over or be equal to each other, the lower and the upper. And if that's the case, then we must not have found our value. Right? And if that doesn't work out, then this is not going to be great. The only other question we might have to deal with is what happens if it happens to be when they're equal, I guess. If they're equal to each other, we would check one more time. Yeah, that would be fine. So if we somehow get outside of this loop, we do not hit the return, then it must mean we did not find it, so we do the same as before, we return -1. So there it is, our implementation of binary search. And so, unfortunately, to make this work, we do need to make an array list of sorted values. So we're going to have to implement one of these sorts on our array list to make this work. So right now, let's go ahead and make a sort for our array lists. And what we'll do to make this a little bit easier for ourselves, let's just pick one of these sorts, and I'm going to go ahead and do the insertion sort. And I'm just going to copy and paste it, and then I'll change the array references to array list references, and it'll work without a problem. So here we go. Let's go back to our thing. Let's implement this, and let's change this. Instead of being an array of integers, we'll say an array list of integers. Oops. There it is. And then that's ARR. So now we have to say size, and there it is. And then we can't say array at j. We have to say array.getJ. Right? And then, of course, we can't say array at j minus 1. We have to say array.getJ minus 1. And then we can't say array at j is equal to that. Instead of saying an assignment, we have to say array.set array at j. We have to say the array at j is equal to the value at j minus 1. So array.get j minus 1. And there it is. Right? So we're setting the jth position to the jth minus 1 value. There it is. And then, of course, we can't do an assignment here. We have to do array.set. And let's make sure we're doing it right. So we're changing j, so .set j to the val. And there it is. So there's our implementation using array lists as opposed to arrays. And again, the only difference is we use methods instead of the bracket notation. So it's very, very simple. So let's hopefully this works. We'll verify it, of course. Here's the original list unsorted. We'll print out, we'll call the sort. So we'll say insertion sort on the list. It'll change the list, right? And then we'll print out the same list, and hopefully it'll be in sorted order. And then let's verify this. Let's run this real quick just to see. And there it is. Notice how it is nice and sorted. So it's perfectly sorted, which is fantastic. And of course, the last step is instead of doing this, so let's be smart about this and put this afterwards. And let's go ahead and do a binary search. And so we'll do the same thing, and we'll say binary search. And of course, and I'll say binary found, just so we can see something different. And again, the reality is we didn't find, it's the same numbers, but there's no 17, so let's run it again. And so we did something wrong. We must have done something wrong, because if you notice, it found a 17 in the linear search, but it did not find it in the binary search. So I did something wrong in my implementation, because it should have found the 17. And in fact, it should have found it at 0, 1, 2, 3, 4. It should have found it at index 4, but it did not find it at index 4. So let's go ahead and take a look at what mistake we have. And it's probably a very silly one, so let's give it one moment to take a look. And I believe it is just like I said, this less than should be a less than or equal to. We should include this because otherwise it will cause a problem. We want to do the one last check. If we land on that midpoint one last time, if lower and upper are happen to be the value, then this would handle that gracefully. So now I believe it'll work. So let's go ahead and run it and find out. So here it is. It found a 17 at 22, and there it is. And the number's not going to be the same number, but it shouldn't be a -1 is the key, because here they're in order. So if we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There it is. All right, let's run it one more time. And there it is again at 10. 1, 2, 3, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's try a different number just to verify. Let's in fact look for a number that we can't find. We know we're never going to find 200, so let's run it, and we should get -1 every single time. And there it is, -1. We run it again. There's -1. And now let's try another number. Let's do 86. So, oh, we did something wrong. Because here's 85. Or, so is there an 86? Let's look for it. So there isn't an 86, and yet found at index 30. So maybe there was something wrong with our linear search. That's odd. This is correct. There is no 86 in our implementation. Here it says found at index 30. Oh no, am I crazy? I'm sorry. We're looking at 17. Oh, that scared me. So yeah, we should put the same number. Let's put the same number. And we should get a -1 for both when we had it. So 40. And there it is, right? 86, the 40th index. Here it happens to be at 8. So let's run it again. 43 and 27. And there is the 86. And of course, one more time, let's see if we can get negative numbers. And there it is, -1, -1. So the takeaway in this video, searching for information is useful. And so what we have to know is, well, when do you use each? The simple rule is, if this data is sorted, binary search is the better choice. If the data is not sorted, the only choice is linear search. You cannot use a binary search on unsorted data. Then the question you ask yourself, is it worth sorting and then using binary search? And the answer is, if you're going to search many, many, many times, you're going to constantly check for values, then it is worth sorting and then using binary search, because it pays off, because each binary search is fast and the only expensive part is the sort. If you're going to only search one time, then it is very likely that the linear search is the better choice. But again, you first ask, is the data sorted or not? If it's not sorted, the only choice is linear. If it is sorted, are you going to do it a lot? Then maybe it's worth using binary search. So I'll see you in the next video. The next video, we're going to begin a new topic of two-dimensional arrays, but that's not too difficult because we've already seen arrays, and we just kind of expand on that idea very simply. So if you have questions, please feel free to reach out to me. But this is a very powerful tool that we have in our arsenal for finding data, manipulating data in a meaningful fashion. I'll see you in the next video.